Welcome to this last session today. Bjørn works at Dyalog, but in Denmark at Insight Systems, and he joined Dyalog at the same time as Morten and I. And he's one of the rare kind of people who does both C programming and APL programming and makes a combination of that work. He's responsible for SQAPL and also Conga. And when we had commissioned the cryptography library from Peter Michael Hæger, we got it. It was wonderful, but we didn't understand anything about it. So how can we actually sell it or document it or do stuff with it? So Bjørn has now spent a year with the Danish Technical University taking 2 courses in cryptography. So he's now ready to teach the rest of us about what it is. So this is Cryptography 101. Take it away.
Thank you. Just to start, I'm not an expert, but I'm getting so good at cryptography after a while that I can kind of understand the answers Peter Michael Hæger is giving me when I'm asking him a question. So, but I'm not an expert. But I will try to. What I will try to do is giving you an introduction to cryptography in the way how it can be used and where you can use it. And I will skip a lot of the details, especially the math. And I will try to be as precise as possible, but sometimes it will slip. And that is to give a better overview of things. So you can probably find mistakes, but they are there because I want to keep the overview. The goals of cryptography is, first of all, what we all know is to keep things secret, manage who can see our data. But a thing that is at least as important as keeping data secret is to do some authentication or data integrity. We want to make sure, or we want to detect if the data is intact, and also authenticate it to get the data and see where we have got the data from. And the last thing is know the origin of the data, the non-repudiation. You can think of this as a signature. If you sign a loan document, you should not be able to repudiate that later. And that is what you can do with the digital signatures also. If you read about cryptography on the network or on the internet or somewhere else, this normally is a set of persons that is in the loop. Alice and Bob, 2 persons that want to communicate, either secretly, in some case, or at least authenticate that they are talking to each other. Eve is normally a person that is passive, but is listening into the communication, trying to decipher what the Alice and Bob is talking about. And Oscar is a more, it's an opponent, and a more active person that would actually try to take over the communication, send some information to Bob in the name of Alice. I will use these names. I will try to set up scenarios of what we are doing with the different parts of the concept of the cryptography, and use the names of persons so you can see what scenario they are actually working in. What do we have in the toolbox? We've got hash functions, symmetric encryption, and asymmetric encryption. And hash functions is kind of like what Charles was talking about. It's the DNA of a text. It's a way to identify the text in a short way instead of comparing all of the text. Symmetric encryption is encryption where we are using the same key on both sides. Asymmetric encryption is where Alice and Bob have 2 keys each, a public key and a private key. I'll get into further details. A hash function. It's like the human genome, a whole lot of things is compacted to one ID of this text. a more mathematical definition of that, is you have a projection of infinite number of bits to a finite number of bits. And the hash functions are constructed in a way that if Oscar sees a text sent to Alice, he cannot kind of just tweak the text so it would have the same hash value as the text that originally was sent to Alice, or Alice sent to Bob. And it's also, you cannot find the collision, so Oscar cannot easily find two texts that have the same hash value or the same DNA of the text. There's some normal way or normal hash algorithms that you have probably heard about before. A lot of them are old. I've put the SHA-256 in bold because that is the one I've chosen to use in an example later. We have the hash function. Everybody can calculate the hash over a text. But sometimes it would be nice to add a key also. So we will get what is called a method authentication code. That means that when you have the text and the key, you generate a hash value. And only the persons who have the key can verify this authentication or this hash value. So this is used when you want to make the hash value specific to a specific key. Symmetric encryption. Both Alice and Bob are using the same key for the encryption. This means that Alice and Bob share one key, and Alice can use that for encrypting stuff, and Bob can use that to decrypt it. And I have put up some known algorithm, type algorithm for symmetric encryption. DES and triple DES is kind of old and obsolete, and the new ones are Blowfish, AES, and Camellia. I've chosen AES for the example later. It's actually American encryption standard, so it's kind of a standard. Asymmetric encryption. This is where Alice and Bob would have two keys each. Alice would have a public key that she can show to everybody, and a private key that only she can have. And Bob would have the same, a public key and a private key. Private keys are, of course, kept secret because that is kind of your key to your data. If you take some data and encrypt with your public key, you can decrypt it with the private key. If you take some data and encrypt it with the private key, you can decrypt it with your public key. So this is a way that you can make different scenarios to obtain some of the authentication and non-repudiation and integrity also. This is kind of the same, that public keys are, of course, the public part. Everybody can see them. Private keys are kept secret. If Alice takes her private key and encrypts some data, everybody can decrypt it with her public key because they know her public key. If Alice encrypts with Bob's public key, only Bob can decrypt it because he is the only person having his private key. There are a couple of ways of doing asymmetric encryption, and there's ASA, that is the one I've chosen to use today, DSA, and elliptic curve. All of these are based on some difficult number problems and giving the security in the encryption. When to use and why to use symmetric versus asymmetric. The speed, the symmetric encryption is fast because it's easier to do. And the asymmetric is slow because it's involving some big numbers and prime numbers with 248 bits of numbers, 2 to the 248 bits. Number of keys. If you are going with the symmetric key, you need a key per pair of person that needs to communicate. So you will end up with many. And if you are with the public key, you only need 2 keys per person, a public key and a private key. So if you only have 4 friends, you can stay with the symmetric case. But if you then get more friends than 4, you will have to switch. And you also, if you only have 4 friends and stay with in the symmetric case, you would have a problem with distributing the keys. The asymmetric case is simple. You just send your public key to whoever wants it, because it's a public key. But in this case, you need to keep the symmetric key secret. So you need some way of communicating with Alice and Bob. Need some secure way to communicate, to exchange the keys before they start communicating with the secure key. So they need another way of communicating than the symmetric encryption that the keys is generated for. Authentication. What does authentication mean? In this case, what we are doing here is we are generating a MAC code. That is actually what we are doing is we are calculating a keyed hash over some text. So Alice can take the text and the MAC code and send to Bob. Bob can read the letter from Alice, and he can calculate the same hash, the same keyed hash over the text, and verify the MAC code that Alice also sent him. So Bob would know that this message is coming from Alice, and he is sure that, or he would know that it's coming from a person that actually have access to Alice and Bob's symmetric key, because that's the only way to calculate the keyed hash. So this means, in this case, Eve would be able to read what is in the letter, but she is not able to know whether it's a real or a fake message. That is only Bob that can verify that this message is actually sent by Alice. Oscar would not be able to send any messages in Alice's name because he haven't got the key, so he cannot do anything to send a message to Bob that Bob would think was coming from Alice. In the asymmetric case, where you have authentication, Alice would create a signature on the text she is sending, the data she is sending. She would calculate a hash, not a keyed hash, just a simple hash, and then sign it with a private key, which would generate a signature. Alice would then send both the signature and the data to Bob. Bob can calculate the hash over the data and decrypt with Alice's public key, because he has Alice's public key, and verify that the hash that he have calculated and the hash that Alice have signed actually is the same. This also actually gives the non-repudiation, because Alice is not able to, or cannot claim that it is not a message that she have sent, because this data, or this hash, have been signed with Alice's private key, and the only person who have Alice's private key is Alice, of course. So in this case, Bob would be completely sure that this message is from Alice. But still, the data is not encrypted. This is just the authentication part of it. The text is going back and forth without any encryption. This is just the authentication, so we can make sure that the message is coming forth in good shape. Nobody have tampered with it, and we can actually verify who's sending it. Secrecy. In the symmetric case, it's kind of easy. You take the plain text, the thing that Alice wants to write to Bob. She would encrypt it with the key, that is the symmetric key that Bob and Alice have shared together before, and generate a ciphertext and send the ciphertext to Bob. Bob would take the ciphertext and the symmetric key and decrypt it to plain text again. Neither Eve or Bob would be able to read the message. No, Eve would not be able to read the message because it is encrypted. And Oscar would not be able to send any messages to Bob because Oscar haven't got the secret key between Alice and Bob. Bob would be kind of sure that, or Bob would be sure that this ciphertext is coming from Alice. But it is not called non-repudiation, because what you need to have for non-repudiation is actually you could prove to third parties that this message is coming from Alice. And if Bob was supposed to prove that to a third party, he would actually have to disclose his key. And he should not do that in this case. So this would not give, it would give authentication that this text is coming from Alice, but not non-repudiation. In the asymmetric case, you could take the public key, Bob's public key, and encrypt the message that you want to send. And Bob can take his private key and decrypt the ciphertext. As we saw before, if you're using asymmetric encryption, this would be too slow because the asymmetric encryption is very slow on large amount of data. So and actually a lot of tools that you have today would not allow you to encrypt free-sized plain texts. So what you would do, or what Alice would do instead, is that she would generate a symmetric key, a random symmetric key. She would take the symmetric key and encrypt all the messages that she have for Bob. And then she would take Bob's public key and encrypt the symmetric key. So she have an encrypted symmetric key and send both the ciphertext and the encrypted symmetric key to Bob. Bob can then take the encrypted symmetric key, and he knows that he have to use his private key to unlock the symmetric key. And when he have the symmetric key, he can take the symmetric key and decrypt the ciphertext to the plain text. Is there any problem with this? Yeah, there's a problem because Eve cannot listen in because she haven't got Bob's private key. So Eve is kind of out of the loop. But Oscar, what could Oscar do? Oscar could actually do exactly the same thing. He could generate a symmetric key. He could take the symmetric key and encrypt some plain text, some message he wants to send to us, to Bob. And since everybody knows Bob's public key, he could take Bob's public key and encrypt the symmetric key and send things to Bob. And Bob would not know where this is coming from. So both Alice and Oscar can send to Bob. So to kind of make sure that Bob knows where this data is coming from, Alice have to add a signature. So she would have to generate a symmetric key, like before. Encrypt the symmetric key with Bob's public key. Encrypt all the plain text that she have with the symmetric key. And then, as a last thing, she would have to calculate a hash over the plain text she is sending with her private key to generate a signature. And what Alice is sending then, she's sending the encrypted symmetric key, the ciphertext, and a signature. What Bob does when he receives this message, he does exactly the same as before. He would use his private key to decrypt the symmetric key, to have the symmetric key. Use the symmetric key to decipher the ciphertext to a plain text. And then as the last thing, he would take the plain text, calculate a hash over that, and verify that against the signature that Alice, decrypt the signature with Alice's public key, and verify that against the hash he calculated. In this case, Bob knows that this is coming from Alice, and it is, and she knows it's for him. So this actually gives the signature gives the non-repudiation that Alice cannot deny that she have sent it. And if Oscar sent it, this signature would be wrong because Oscar haven't got the private key of Alice. The problem we have is the key problem we have is how to keep the keys safe. And there are different ways to do that. There's the Windows Certificate Store. That is provided under Windows where you can actually store your certificates, and your certificates or the private key would be kept in a store that is not accessible for. You can store it in the store in the way that it's not accessible to the private key. And there's also the PKCS #11. PKCS is public key cryptographic standards. There's a good description of that on the internet on what that means. And this is if you have your key on a smart card. Both these two actually comes with a downside because they have because they are not letting the key out. They also decide what kind of algorithm you're allowed to use. So you cannot freely choose what hashing algorithm you want to use and what kind of asymmetric encryption you want to use. They are kind of limited by the cryptographic provider that you are using on either PKCS 11 or Windows Certificate Store. You could also keep the data in APL, in a component file, in a PK#C8 structure, which is kind of the secret, the private key covered in a bag with a paraphrase or a password. That is also the way that if you buy a new certificate, that is the way they are sent, either as a PK#C8, as now #8, or 12. If you choose to have them in APL, you can use the Dyalog Cryptographic Library, which is a set of cover function for a interface to OpenSSL, the OpenSSL library. And it provides a huge set of hashing function and encryption function. It have tools to work with certificates, and we have actually ported it to all platforms, both AIX, Linux, and the Raspberry Pi and Windows. I do not recommend kind of moving these applications between Unicode and Classic because that will cause some problems. You have to choose one platform or one type of interpreter and stay there. This is what I said. This is a certificate store. You can store the store certificate and keep the private key secret, but there's a limit to the limits on the available algorithm. We do not have too many tools to access the certificate store from Dyalog, but Microsoft.NET have some, and Conga also is at least able to read the public part of the certificate out of the certificate store. And Conga can also ask the certificate store to use the private key when you are making connections to a HTTPS server, a secure server. Samples. I thought I would try to make an example of what to do or how you could do it. So I looked at we have an OO example with a keyed component file where you can, instead of using index, you can use keys. And this is kind of, I think you have seen it somewhere else, or somebody else using the same method of indexing into a variable. What I've done is I've kind of extended the keyed component file to also handle encrypted and compressed components. We will start with just encrypting the components. If we want to have encrypted data in a component file, we will need to add some information, some extra information to the component file, so we have that information, the needed information there. We need to add some user information, some information about who's who, and we need some access information about which users is allowed to access which keys. What we need to describe a user, the user information would be a matrix, and this is the columns in the user matrix. There would, of course, be a user ID, a public key, and a private key. But to keep, we cannot just store the private key in the component file, because then everybody could just read the first component and read the private key out of there. So what we would do with the private key, we would take a password from the user. The password, of course, we will not store that. The user have to supply every time he is accessing the component file. Some sort, that is to add some random stuff before you. We need some random stuff to give the process a certain amount of randomness. We will add some repetitions and an initial vector. This is all kind of things that we use to we will derive a key from these things and the password that we can use to encrypt our private key so it's not accessible. But in general, it is just to have some things that make sure that if two users actually are using the same password, they would not be able to see it because we have some extra randomness in the loop. What do we need to add to keep track of the access information? We have the two simple thing is, of course, user ID and the key. So user ID BHC would have access to key A, key B, and key C. Key C. What we need to add more, we need to have a symmetric key, an initial vector, and a hash. And all of this we will catenate together and encrypt with the user's public key. We will use the symmetric key and the initial vector to encrypt the component with a symmetric encryption cipher, because the components can be large, and we need to do that symmetrically. Use symmetric encryption for that, and to use a symmetric cipher, we need a symmetric key and initial vector. The hash is to actually verify that it's the content have not changed. I will try and go through some of the main functions in the sample before I'll trace through the sample. When you create a new component file, and when you open a file or create a component file and the user is not there, you will have a user and a password or a paraphrase. And when we are adding a user, the first thing we will do, let me just, before I go further, I have kind of taking all the cryptographic things I am doing and kind of lifted them up of the function, so it should be more easy to see. This is just a small cover function to calling into the Dyalog Cryptographic Library. But the first thing we would do is that we generate a asymmetric key pair of a certain size. In our case, it's 2048. We will generate some random sort, random initial vector, and some repetitions. This is all the information, most of the information you actually saw for the user, the columns in the user matrix. We would use the paraphrase or the password that the user provided, the salt, the number of repetition, and the cipher key, of these three, to derive a key. This is done in a standard way. There's a standard way to generate these keys from a password. That is called a password-based key-derived function. And that is actually also the same that you're using on the Wi-Fi. When you're entering these access code to Wi-Fi, it is based on the same mechanism as this one. When we have the derived key, this function can actually, from these, generate a key of a certain size. I know that we need exactly this cipher key size for the derived key. So this would generate me a derived key of this size, which is 32 in our case. We would take the derived key and the initial vector and encrypt the private key to the encrypted private key, and we will add all this information at the bottom of the user matrix. We will come back to this when I trace through the example. When we are adding a new component, we will serialize the APL data. We will compress it. So we have the type and the what I call the plain text. It's now a serialized compressed APL data, but for me it's kind of the plain text because it's before we encrypt it. We will generate a random symmetric encryption key, generate an initial vector, calculate the hash over the plain text. Then we will find our user. So we have which user we are working as. We would encrypt all the plain text with the symmetric key and the initial vector, so we have a ciphertext. And then we would take we'll take the public key from the user, and then we'll take the symmetric key, the initial vector, and the digest, and encrypt it with the public key, and put it into a container which is encrypted, and just catenate that to the access. So we would know next time we see the access, this user have access to this key, and this one contains the encrypted format of the symmetric key, the initial vector, and the digest that he can unpack because he can get access to the private key of. This is encrypted with the public key, so he can decrypt that with decrypt this one with the private key and get these three things that he needs to access a component. Reading a component. We get the data, which is the type and the cipher. The type I'm using to know whether I have to decompress it also or it's just a serialized format. Get access. I will have a user, a key, and a paraphrase or a password. And from that, get access will provide me the secret key, the initial vector, and the digest. Then I can decrypt the ciphertext with the secret key, or the symmetric key, and the initial vector to a plain text. And I can decompress and deserialize the plain text to an APL. This one, we need to look a little further into. The get access. This will find the user. If the user is not there, we'll signal an error. We will make sure that the user have access to this key. If the user haven't got access, we'll kind of signal another error. If it succeeds, we will get all the information from for the user, and we will derive the key the same way as when we added the user from the password, the salt, the repetition, and the cipher size of the key. So we can decrypt we can take the encrypted private key and decrypt it with the derived key, so we have the private key. When we have the private key, we can decrypt the access info that we have taken from the access matrix and split that into the symmetric key, the initial vector, and the hash. Replace component is close to the same, except that if you replace a component, we will keep the secret key. We will not generate a new symmetric key for it. We'll just get the secret key that is kind of set up for this component, and it just encrypt the new data with the secret key that we have for this component. Maybe you should get back to this after we have traced through. But this is actually the way that you can give access to another user to a component. So I think we'll get back to that and try and trace through some of the code. First of all, we need to have a file name. I will delete the file name if it's there, so we could see I'm starting from scratch. Generating a new file, I will create a new encrypted file with the file name, the user ID, and the password. That will get us into a constructor. This is initializing the Dyalog Cryptographic Library. This is kind of taking the arguments that I gave along to when I created the instance. You should notice that I have not set compression yet. I'm just using encryption right now. We are putting file type in the first component, keys in the second component, user in the third, access in the fourth, and reserve the fifth for extra things if we have to add things. We will try to find the user, but since this file is new, there is no user, so we will have to add the user. And this is the function that I showed before in PowerPoint. We will generate a symmetric key pair. You should notice that this is actually taking time to generate that. That is doing all this kind of weird math with the prime numbers. Now we have a public key and a private key. We will generate some random sort, a random initial vector, and set the repetitions. And we will derive a key. If I'm lucky, you'll be able to see this is a shape 32 random vector of characters. This is bytes from 0 to 256, 255. I would take the private key that we have generated. That is actually quite large. That is nearly 1,200 bytes. And encrypt that with the derived key and the initial vector. And add all the user information to the user matrix. And of course, remember to write the information about the users back to the component 3. Any questions?
The private key is in the memory.
Yeah.
What are you doing about that?
That is a key problem. If you want to decrypt stuff, then you have to have the private key in memory at some point. Yeah, how long? You cannot get rid of that problem. But if you have enemies that can create a memory dump or core dump of your APL, having the key in memory is a problem. But on the other hand, normally you would kind of restrict that. There would be a very restricted set of persons that can do that.
It's a similar question, but in a namespace, is there a way to secure a namespace when doing this, like a locked space? If your session dies and a continue workspace is saved, for example, it would be a namespace that nobody could get into that might have some of the variables laying around, or I don't know.
No, we don't have that.
What I was hoping for was a mechanism that you create a variable which of some sort can be made disappear, really disappear, when you're ready.
Yeah, we have talked about that. And my first initial try at that was just to simply using index to override the variable. But it's kind of not safe to do it that way, so we need to make some changes to the interpreter to actually have a pocket in the interpreter or a variable that kind of get expunged in the real way after it's stopped. We have been stopped using it, or that I can control is deleted when I've finished using the private key.
Bjørn, it looks very much like Microsoft.NET assemblies. Probably cryptography provides very much the same functionality. Could you compare your approach and the Microsoft approach? What's the difference and the goal?
Most of the ciphers and the hash functions and stuff is exactly the same, because you have to be able to encrypt on Windows and decrypt on Linux if you're using public-private keys. So most of the stuff that is in .NET, you can use from APL also, and should generate close to the same thing. We have chosen to provide an interface to OpenSSL because we can port OpenSSL to all the platforms, and we can provide the same functionality on all platforms. We cannot port .NET stuff to Linux or to the Raspberry Pi. So that's the reason we have gone that way.
Is the library available?
Yeah, it is. I would guess it's a yes. Yeah. But there could come changes to it. But that's a thing you have to live with.